Good day everyone, I am Lat Kinsley Aaron and I am here to slightly discuss and give examples of first-order differential equation, elementary application of differential equation, and higher order or general linear homogeneous differential equation with constant coefficient. Let's proceed. First, let us know how to solve a first-order linear differential equation. A DE is said to be linear if we could put the equation in these forms. If we can rewrite the DE in this form, then we can say that the DE is linear in x or y. If a DE is linear in x, meaning we can express the DE in terms of this form, then use these formulas on the right. Let's start with an example. So our goal here is to transform this DE into a formula a while ago that is linear in y. We can do that by multiplying the whole equation to 1 over x. So let's copy first the whole equation, then multiply it to 1 over x. Then we will have the answer of dy over dx plus 1 over x times y is equals to x squared. Now, as you can see, we can now get the values of px and qx. The value of px is 1 over x, and the value of qx is x squared. Now that we have the values of px and qx, we can now use the formula on the right a while ago. So now, what we will do is we will copy the formula and replace the px and qx with the values that we got a while ago, with px being 1 over x and qx being x squared. Now, we can simply continue evaluate this. And as we can see, there is a value of y e raised to ln x. We can simply cancel the e raised to ln, and the only term that would be remaining is the inside function of ln, which is x, and it will simply just go down. So, our solution would be xy integral of x cubed dx. Integrating this, we can get xy is equals to x raised to 4 over 4 plus c. So this equation is now complete, but we can still rewrite it into different equation like xy minus x raised to 4 over 4 is equals to c. Or, in terms of y, which is y is equals to x raised to 3 over 4 plus c over x. Let us now proceed to elementary applications. For our first problem, radium decomposes in air at the rate proportional to the amount present. If initially there are 20 grams, and after 10 years, 0.6% of the original amount decomposed, A. Set a model that will predict the amount of radium at any time t. B. What is the half-life of radium? And C. What is the amount remaining after 900 years? After inspecting the problem, here are the gathered information. Given x is equals to the mass of the material and dx over dt is equal to the rate of the decay of mass. In order for us to do letter A, first, always set up the equation. We have the equation dx over dt is equals to kx, and if we perform separation of variables, we can get dx over x is equals to k dt. We can now integrate both sides of the equation. After integrating, we can get ln x is equals to kt plus c. Now, we can exponentiate this equation. Cancel e raised to ln and we can get x is equals to e raised to kt plus c, and it will be x is equals to e raised to kt times e raised to c. Now, we arrive at a general solution of x is equals to c e raised to kt. Using the general solution, we can get the values of c by substituting the values with the given we got a while ago. Since e raised to k times 0 is equals to 0, we are now left with c is equals to 20. Since we have now the value of c, we can now find x by subtracting c, which is 20, to 20 multiplied to 0.6% or 0.006, which is equivalent to 19.88 grams. Since we have now the value of c and x, we can now substitute this to the general solution. Doing so, we can now find the value of k. Using calculator, the value of k is equals to negative 6.02 x 10 raised to negative 4. Since we have now the value of c and k, we can substitute this to the general solution and we can get the answer in A. This will be now the model that will predict the amount of radium at any time t. In solving letter B, since the half-life of 20 grams is 10 grams, we can now find the value of t by substituting the values in our model. We arrive at an answer of 1151.78 years. In letter C, using t is equals to 900 years, we can find x using the same model. Using calculator, the answer would be 11.64 grams. Let us now proceed with higher order or general linear homogeneous DE with constant coefficient. In order to solve this DE, first we need to convert this into the differential form. We can substitute this into d cubed multiplied by y plus 4d squared multiplied by y plus dy plus 6y is equals to 0. Now, we can factor out y so it will be similar to the differential form. What I'm going to do next is we will let this d equal to m. Now, we need to find the roots of this polynomial. All possible roots is given by the equation p over q. So what will happen here is now we can now do synthetic division. Using number 3, let's perform synthetic division. We first copy the coefficients of each term. Bring down 1, multiply it to 3, it will be 3. Then we can add 4, and it will be negative 1. We multiply negative 1 to 3 and it will be equal to negative 3. Add 1, it will be equal to negative 2. Negative 2 times 3 is equal to negative 6. Add 6, then it will be equal to 0. Therefore, one of the roots, or m sub 1, is equal to 3. We are now left with m squared minus m minus 2 is equal to 0. If we are going to factor out this, then it will be equal to m minus 2 times m plus 1 is equals to 0. Now, the roots will be m sub 2 is equals to 2 and m sub 3 is equals to negative 1. So what are we going to do now is that we will now write it in the form of y is equals to c sub 1 e raised to m sub 1 x plus c sub 2 e raised to m sub 2x plus c sub 3 e raised to m sub 3x. This will now be the answer, but you can also write this in this form.